Okay, so if you go back to question 1, we'll just go through these in class. So look, folks, nobody should be chatting. Now, I'm aware when I was going through that, there were people who were sitting talking. So let's just cut that out. So, A and B. Let's see, what do you think A is? Atrioventricular valve. And B then, we've already talked about it, it's the left ventricle.
Can you call it the AV valve or do you have to say the full name?
Well, looking at Mark's scheme for a couple of years ago, they've put AV valve, but look, you know, I would give it, to be safe, give it the full name. Okay, draw arrows in the diagram. Look, this is one big issue. A lot of people look at questions and they see, okay, your eye just automatically drops down to the spaces there, and you go to write something in, and then the next space is part B. But if that's the case, you'll have lost 2 marks because you've missed out on part 2 there. Draw arrows to show the path taken by the blood returning from the body organs. So returning from the body organs is coming up through here. Okay. And going into the atrium there, down into the ventricle, and where else, what's it saying? Before going to the lungs. So it's going to the lungs up through there. And name the blood vessel in which deoxygenated blood travels from the heart to the lungs. So it's this blood vessel here or this blood vessel here. They are the pulmonary arteries. The only artery in your body that carries deoxygenated blood. And if I can rub off. If we look at the diagram there, the thickness of the 2 atria is the same. Whereas the thickness of the muscle in the ventricles is you're used to.
I can't create a station based on that.
That's my watch talking to me. Has anybody worked out how to stop their Apple Watch talking to them, even though it's on silent?
Yeah,
how?
There's a dead silent mode, but I can't remember it.
Wee bit louder?
You have to go on the settings, but like a dead silent mode on it, so it doesn't disturb you.
I'll get you to show me sometime. I have it on silent, but it's still talking rubbish. Okay, so where do you reckon this is cut? So if you look where the valves are here and here, here and here, and then we've got valves there and there and there. So basically this cut has been done there. And then they're looking into the heart. So they've cut across and they're in here and in here. It means there's going to be less blood there. Less blood getting pumped out in each heartbeat. Why would someone with we diagram that into the hypertrophy? Okay, we'll come back to that a little bit. Let's move on to question 3. So what's the term for the phase of the cardiac cycle during which heart muscle is contracted? So what's the name for that? Systole. Okay, we were talking about the thickness of the different walls and how the thicker the wall, the greater the pressure. And if we look at this graph, before we look at the question, let's just have a look at the information there. So the left ventricle creates the biggest pressure. Where is it pumping blood to? All around the body. The right ventricle is pumping it to The left atrium is pumping it to, and the right atrium is obviously pumping it to the right ventricle. So using your understanding of the structure of the heart chambers, why is the maximum pressure in both atria the same, whereas the pressure in the left ventricle is much pressure than the right ventricle? So we've got two questions here. So let's look at the first one. So that's talking about atria. When we looked at the diagram, put that information in context, we're saying the pressure in the two atria is the same because they have the same thickness of cardiac muscle. So therefore it's going to contract with equal force. Forcing the blood into the ventricles. If you just say the atria have the same pressure because they're forcing the blood into the ventricles, you're not going to pick up 2 marks there.
Can you repeat again?
Yeah. So we're saying the atria, the two atria are the same, have the same thickness of muscle. So therefore, it's going to contract with the same force. Pumping blood into the ventricles. So there's a lot of information you've put in there. You've mentioned the thickness of the muscular wall. And that's going to, because they're both the same, you're going to get the same pressure. And you're saying where the blood is going to be travelling to. The next part of the question is basically, why do you have a greater pressure in the left ventricle compared to the right? So what causes the greater pressure? The muscle. So you'd say the muscle in the left ventricle is much thicker than that in the right. Okay. Therefore, the force of contraction in the left is much higher to create a higher pressure to force the blood through the capillary networks of the organs of the body.
Could you repeat the first bit you said after the rest? Just the first bit.
Which bit?
Just the first bit you said?
About that bit or the atria?
No, that question there.
Yep. So we've said, basically you're saying that there's a thicker muscle in the left ventricle, or the muscular wall is thicker in the left ventricle. And so therefore there's going to be greater contraction, which is going to create a higher pressure, because that's needed to force the blood through the capillaries of the body's organs. Whereas you can add in there the right one only has to force it through the capillaries in the lungs. To the heart. Okay, this is a bit of a strange diagram then, question 4. It tells you the heart has been sectioned. What does that mean? Sectioned means it's been cut. In a particular plane, in other words, a plane is like a direction, a level. All 4 valves can be observed. So if we go back, so we've got 4 valves. The two big valves are the atrioventricular ones. So obviously there's one and there's the other. And then these are the valves going to the aorta and the pulmonary artery. Does that make sense? So this is the right atrium. So this is going to be the left side of the heart. Okay. And as we said, those are the atrioventricular valves. So what are the parts labelled A and B? So if we look at A, as we said, it's an atrioventricular valve. Okay. And B, then, they are the semilunar valves. They're not asking you to say which one is in which. So basically, if you just label that as a semilunar valve or arterial valve. Yeah. Okay, describe the state of the valves. What do we mean by the state of the valves? Open or closed? And suggest which stage of the cardiac cycle is represented. So, atrioventricular valves, do they look open or closed?
Open. No, because see those lines there, like back, and there's a hole. Whereas the other ones are like, is that not the valve closed? Like that was it?
Straight over to the
Yeah, that's closed. It's closed. And then that one there is like the hole where the blood can wash. So that's like
Right, I'll tell you what the mark scheme says. This is a difficult question. So it's saying the ventricles are contracting from the bottom up, and that increases the pressure in the ventricle, forcing blood upwards. To me, it's a pretty bad question.
So that means that the
Oh, hold on. No, sorry, I'm in the wrong bit. What do we say? If we look at these valves here, are they open? If we look at the AV valves, the atrioventricular valves, can blood get through there? Yeah. So they're open. So the atrioventricular valves are open. What about semilunar valves? What are they? Closed. When are the AV valves open? So it could be, I'm just jotting a few ideas down, atrial systole, okay? When the atria are contracting, forcing the blood through. What normally happens after that, you've got ventricular systole, which pushes those valves closed, and then it will open it'll force blood into the arteries, it'll force open the valves at B. So you could say that it's at atrial systole, the atrioventricular valves are open and semilunar valves are closed, therefore it's atrial systole. So you get 1 mark for getting all of that and 1 mark for saying that. Or if you think after the ventricles have contracted, so after ventricular systole, what's the stage? Diastole, yeah, or diastole. And that is whenever the atria and the ventricles are relaxed. The AV valves are open at that point. they open during the relaxation of the heart. And the other valves, the arterial valves, the semilunar valves there, will be closed as well. So they're going to give you either atrial systole or diastole. Okay? Cardiomyopathy. Valves help to maintain one-way flow of blood through the heart. How does blood leave a ventricle? So, ventricle contracts. Where does the contraction start? Bottom. So when the ventricles contract, that increases the blood pressure in the ventricle, and the blood is forced upwards. Into where? Aorta and pulmonary arteries. But it only gets into the arteries whenever what happens? Semilunar valves have to be forced open. And that's whenever the pressure in the ventricle exceeds the pressure in the arteries. Now, it says valves, so we've talked about the semilunar valves. What do we need to say about the atrioventricular valves? They're forced closed because the ventricular pressure is greater than the pressure in the atrium. Okay, hypertrophic cardiomyopathy is not something you're expected to have heard of. It's not something that's mentioned on your specification. So sometimes you get words that look a bit scary. It's telling you it's a condition, and that someone with hypertrophic cardiomyopathy would have a thicker muscle in the wall of the ventricle, and that reduces the space inside the ventricle. So if there's less space, they have dizziness or fainting or tiredness. Yeah. So the explanation would be there's less blood being pumped per heartbeat. Therefore, less oxygen will reach the brain and other tissues. And that's going to lead to the dizziness and the fainting. Okay, so describe question 5, wave of excitation. It says it originates in the sinoatrial node. So because they have given you that information, you can then refer to it just as the SAN. If they didn't give you that information, you would have to talk about the sinoatrial node. And then after that, you could talk about the SAN. So how does this? It originates in the sinoatrial node. You need to discuss what happens, and at the end of your discussion, you're talking about the ventricles contracting. So basically, you'd say the SAN sends a wave of depolarization, or, well, probably you're going to call it excitation. Across the atria, and that causes them to contract. Right, I'm putting this in bullet points. You need to get all of that to get 1 mark. So you're saying, it talks about the wave of excitation originating in the sinoatrial node. So you're saying that passes across the atria and results in atrial contraction. What are you going to mention at this point? Pardon? Before we talk about the AV node. Yeah, non-conductive tissue. So the wave reaches what? AV node. Passes down, what's the next structure? Bundle of His, which takes it through the septum. What's next? Purkinje fibers. So it passes up.
Do you not need to stay on the tool on the line? No, it's fine.
What?
I was thinking with some hands now.
Is it all right?
Yeah.
Yeah.
See the bundle of His, does that need capital letters?
Say it again, what?
The bundle of His.
They're not going to take marks off if you don't. So if you look at that, so I'm just going to highlight the key things. So we've got the excitation crosses the atria, that's atrial contraction. If it just said describe how the heartbeat is how it starts from an initiation, you would have to, I would be highlighting the sinoatrial node, but they've given you that information. So that's why I'm not highlighting it. But if they didn't give that information, obviously that would be key. Got the non-conductive tissue. Prevents the wave passing directly to the ventricles. The AV node. Bundle of His. Purkinje fibers. Ventricular systole. Okay, make sure you learn those in the right order and you get them. Did something fall? Oh, it's a bird. Yeah. No, it's just a bird flying at the window there. Okay, so we're going to skip through. Tomorrow we'll look at the ECG. Okay, there's a pretty gory photograph. They've cut through the left side of the sheep's heart. So if we look at that, that is actually the ventricle they've cut into there. We've got, what are these things here? Chordae tendineae. Okay, so those are chordae tendineae. What are they attached to normally? What are they attached to? So papillary muscle down there. And the valve flaps at the top there. Okay, so they've cut into that, all right? So how would you label the different parts here then? So at the top there, A is pointing to the AV valve, atrioventricular valve. B, as we said, chordae tendineae. The atrioventricular valve. We said B, chordae tendineae. C, what do we say for C? Papillary muscle. And D is just the left ventricle wall or the cardiac muscle of the ventricle. So, comparing the left and right sides of the heart in terms of the ventricles, they're different. And you know they're different because one has to create a bigger pressure because it's forcing blood through the capillaries of the body's organs, whereas the other side's only forcing it to the lungs. So you need to pick one thing and say how it's different. So what's the easy one to talk about? Cardiac muscle. That's the easy answer. So you'd say D, cardiac muscle. On the right side it would be thinner because it creates less pressure because blood is only being pumped to the lungs. You could have said the chordae tendineae will be smaller or thinner, or there will be less papillary muscle on the right side again because there's less pressure created because the blood only has to be pumped to the lungs rather than all the way around the body. Okay, the next question is the graph. So, you're familiar with this graph? And you're asked to point out when the atrioventricular valves close. So if you think of structure of the heart, you've got the atria, ventricle, so that's the right, sorry, the left side of the heart. Obviously you've got the same on the other side. These So just recording this. So question 11, we've got a diagram there. It's got solvent front. This is not a SIA exam question. As I said, the SIA, they've actually marked the midpoint or the leading edge for you to measure. But when preparing a chromatogram, 2 precautions. So, Jamie, what did you put?
Wearing gloves.
Pardon?
Wearing gloves.
A bit louder?
Wearing gloves.
Where?
Wearing gloves.
Oh, wearing gloves, yeah. So I just can't hear whenever everybody's got the mask on. So make sure you're wearing gloves. so you don't contaminate the chromatogram. Hannah?
Make sure the origin line is drawn with pencil.
Yeah, make sure the baseline or the origin line is drawn in pencil. So there's your chromatogram. So we've got the origin, we've got solvent front. Mark a letter X to show where the spot for the amino acid A would have been placed. Well, I mean, that sounds a bit strange. It's so easy, but it's down there. Okay. And then calculate the RF value for amino acid B. Now, in this case, they've given you a little scale there. Normally in SEA, they don't. You normally just use your own ruler. So make sure you've got rulers with you. Make sure you've got calculators. And if you measure that, what did you get? Ellie Stinson, what was your calculation?
6/10.
Yeah. So basically, I mean, a lot of people would have read that off as 7, but you had to realize that the origin is at 1, so it is 6/10, which gives you 0.6. So you get 1 mark for your calculation showing that you got 6 and you got 10, and 1 mark for the RF value. Okay. It says, 2 decimal places. So I wouldn't get a mark for that. I need to write 6.0, 0.60. And if you just do it in your head, you only get 1 mark if you get the right answer. If you get the wrong answer, you get absolutely nothing. So make sure you show your calculation. Question 12. How would you prepare and run the chromatogram? So basically add solvent to the chromatography tank and allow it to saturate the atmosphere. Draw a baseline in pencil, 3 centimeters from the bottom of the paper. Add a spot of the amino acid solution to the baseline, allow it to dry, and then reapply. And you do that about 5 or 10 times. Lower the paper into the chromatography tank. Make sure the baseline is above, or the origin is above, the level of the solvent. Leave for several hours. And you remove it once the solvent front is close to the top, but not touching the top of the paper. Remove the paper, mark the solvent front. Somewhere in there you should be saying that you're wearing gloves or that you don't handle the paper or that you only touch the corners, okay? So they've called it a baseline this time. We normally call it an origin, but obviously either is okay. We've got our solvent front. And in this case, they've got 3 spots shown, and they've got the midpoint, which is used to measure the distance it's traveled. So in other words, that is where you're going to measure to. So what did you get your RF value to be? Jordan, what did you get your RF value to be? 0.5. So obviously measuring it, my page, let me see, I haven't got a ruler here, but it should work out at 0.5. So therefore, what did you identify it as? Aspartame. Look, if you get the wrong RF value, shh, quiet. If you couldn't remember how to work out the RF value, but they give you a table. Look, if it totally goes from your head, write down a figure and work out which one it's the same as. All right? So, because there is consequential marking. Okay, let's move on to the heart then. So we'll put the questions away.